Hello. Hi, my name's Daira Emma Hopwood. I'm ECC's R&D Engineering Manager, and I'm going to talk about Crosslink and the future of proof of stake in Zcash. Okay, there you go. So this is all of this research is joint work with Nate Wilcox and Jack Grigg. They contributed some essential ideas to the design. And you can see more information at this URL. Okay. So I'm gonna. So we think we intuitively know what a blockchain is, but it's worth sort of modeling it in more detail. And so I think of a blockchain as having an L0, which is a protocol that allows you to agree on an eventually consistent sequence of blocks, and L1, which is so how do you make an open economic computation out of those blocks? So that's it's a distributed protocol that computes something, and the participants can rely on well-defined rules on what it's computing, and it supports economic actions. So you can hold value, you can pay other users, you can sort of potentially use other financial instruments, and that's also supported by sort of other layers on top, but we're just considering at the moment L0 and L1. And it needs to be open, so that anyone can participate. It has sort of fairly weak trust requirements on participants, and it's robust against attack and failures. And the reason for that is that centralized systems, especially when they're doing something controversial like providing sort of untraceable private payments, privacy is normal, but not everyone thinks so. And protocols that are centralized that try to do that haven't had a good track record of success because people have shut them down. Okay. So yeah, all of these criteria for what an open economic computation is are relevant to proof of stake. So we're going to need to consider all of them. Okay, you may notice that these layers are interdependent. So we're agreeing on a consistent sequence of blocks, and then we're defining the economic computation in terms of that sequence. But then when we're using either proof of stake or proof of work, then we're also relying on those economics to secure the L0. So we have a kind of a cycle here, which is difficult to analyze. And you should be kind of suspicious about this and want to make the analysis quite rigorous in order to make sure that it can't be attacked. And especially during if you're trying to swap out the L0 while maintaining the balances of the L1, then that's an inherently risky thing to do, potentially. But what if you could, instead of transitioning in one step to proof of stake, you could change the L0 so that it's secured by both proof of work and proof of stake. And the idea behind that would be that would resolve your concerns about the security analysis until you can be more confident about them. So why would we like to support proof of stake? So participants can earn competitive revenue by staking and by providing network infrastructure and security, because they're sort of all of the staking participants are following the protocol, and the protocol security is dependent on a consensus of those stakers. It enables assured finality. So in a proof of work blockchain, you can have rollbacks, you can have forks, and you can sort of specify a confirmation depth and not look at the tail of the chain after that confirmation depth, and then hope that the chain before that point is stable. That's what eventual consistency means, but that's only a probabilistic property. And so if you have a way to obtain a final block that's sort of under certain assumptions, can't be rolled back, then well, there are several benefits. You're improving the consistency of the latency of the user's block use of the blockchain, and that can be used to implement bridges between different blockchains that can be made more reliable and secure. And for the protocol that Strada and Nate designed, called Crosslink, there's really no significant UX complication in the sense that you still have a blockchain in the same sense as a proof of work chain, and the final block is just some ancestor of the tip of the chain. And other advantages, so pure proof of stake uses much less resources. It's easier to bring up infrastructure to support it, and potentially it reduces the environmental impact relative to proof of work. Zuko used to be sort of wary of using this as an advantage of proof of stake, because I think he thought it was quite controversial. It is controversial, but I think it's pretty clear from the example of Ethereum that that yes, you can almost completely remove the environmental impact of proof of work for a chain. So in current Zcash, there's a pressure for miners to sell in order to recoup their expenses. And in a proof of stake protocol, so if it's a pure proof of stake protocol, then it replaces that with the pressure to buy funds that you can use to stake. But if we're doing hybrid proof of work and proof of stake as a first step, then so why would we want to do that when it doesn't have all of the advantages of pure proof of stake? Well, it's making progress towards pure proof of stake system. You can it supports both mining and staking, and so it's so potentially less disruptive during the switchover, and so the ecosystem can support both sort of communities of miners and stakers. To me, the most important reason is security. So if you're completely replacing a protocol's L0, then it's an inherently risky thing to do. But if you wait until sort of there's more stake securing the proof of stake layer, then that allows you to be more confident. And in the meantime, if the protocol is designed properly, then well, what I think is properly, then your proof of work layer is still giving you similar security properties. And so in a pure proof of stake system, they're usually designed to use leader election protocols. So instead of so a miner being the next party to find the next proof of work, which is inherently unpredictable, in sort of many of these protocols, the leader is elected for some length of time called an epoch, and during that epoch, which might even be predictable in advance, they're a potential target for attacks. You still have validated buy pressure to buy funds for staking, and we know that it works, that this approach can be, it's been demonstrated by Ethereum so during its transition to proof of stake. Okay, so what are our goals and requirements? So users can stake their Zec, they can earn revenue from it, and provide security to the network. Enable new features, and so you can improve existing use cases. So in the case of a deposit to an exchange, if the exchange accepts the money using this consistent final block, then there's more predictability in how long it's going to take to deposit your funds. And that can potentially be shorter for the same sort of security level. That's a little bit complicated. You can improve the user experience for wallets and the implementation complexity of wallets, because once you know that a transaction is final, it's extremely unlikely that both the assumptions of the proof of work and proof of stake protocols would have to be violated for that transaction to be reverted. And yeah, you don't have the sort of the complexity of that. So for both, this actually applies to both wallets and nodes. It's simpler if you can be sure that the state is not going to be rolled back past a certain point. So do we have any questions so far on the goals and requirements? Okay, so the question is, do you think the change to proof of stake will have an impact on the price of Zec? I do not know. I have no idea. I've never been able to predict the price of Zec. I don't even have a clear mental model about what affects it. Okay, so next question. Do you envision that Crosslink could be a stepping stone for other blockchains, such as Bitcoin, to move away from proof of work? So I designed Crosslink and we designed Crosslink to be quite generic in the components that it uses. And that both has an advantage for Zcash in that so it allows us to defer the decision of what the FT protocol to use, for example. I'll explain that more later. It's just more flexible in general. If there was a security problem in a particular protocol, for example, you could potentially swap it out. So I think that for all the reasons that this has been designed to be an easy way for Zcash to move to proof of stake, it could be applied to Bitcoin. Now, obviously, there are a lot of, it would be politically fraught, to say the least, in the Bitcoin community. But I personally think that it was certainly a motivation for me to give the best way I knew how to do a move from proof of stake to from proof of work to proof of stake in general. Okay, next question. What's my opinion on Ethereum's Whisk? I have not read it, so I won't try and analyze that off the cuff. Oh, look, it's I clicked on it and it's replaced my screen share, but that's okay. Yeah, that's not loading. Oh well. I'll go back to the presentation. There we go. Is that screen share still working? Yes. Okay. And here are the other goals and requirements. So stability and security. We've kind of gone through this a bit already. But so formally, you want to prove that the protocol is rollback safe using assumptions on either the proof of work or proof of stake subprotocol. So there's a caveat there, which is that we only have the same amount of issuance to share between miners and stakers. So potentially, if there's sort of less issuance available for each one of those, then that affects the security. But it only affects the security sort of by a constant amount, and you can reason about whether that's sort of likely to be a problem in practice. As I said, it preserves the current mining ecosystem for now, and so the cost of attack shouldn't be well, we want it to be more secure because we want it to have additional security properties. So assured finality is an extra security property, but for the existing properties, we want it to be no less secure. And we want to sort of rely on the existing consensus design. So the fewer changes we need to make to it, the better. We want staking. So this is a kind of an undecided issue, the extent to which staking should be private. I personally think that it should be possible to stake completely privately. So especially if so you have a validator that is sort of delegating the stake, they should be able to do that delegation privately. There should be no disruption to privacy for the non-staking use cases. And we want to preserve the developer experience. So ideally, there might be some changes to interfaces in order to support staking, for example. But if you're doing something that was previously supported, then you should be able to use the same interface. Okay. So Nate, Strad and I developed a family of designs called Crosslink. They're called Crosslink because they involve sort of cross-linkage between the proof of work chain and a BFT, and I'll explain what that is later. And yep, I did present about Crosslink in a previous Arborist call. This is a slightly streamlined version relative to that one. It's very similar, and the slides are sort of derived from those slides. But I've got an hour here, so I should be able to go into more detail if people want me to. And so this version, it effectively unifies the proposers of blocks in the BFT protocol and miners. And that's actually a huge simplification because so instead of introducing this extra category of protocol participants as well as stakers and miners, that's basically all you need. Therefore, the structure of so how the protocol works is very similar to existing Zcash. It's just some additions rather than any fundamental change to the existing system. So the roadmap spreadsheet that you've seen quite a few times now includes our estimates for how long this would take. And there was a question on Hoover about why we're focusing on this. So basically, the design work for Crosslink is already done. And what we're doing at the moment is writing it up and making sure that it's available for future protocol developments. Basically, we're not spending a great deal of time on TFL on the trailing finality layer at the moment, but we need to put it on the roadmap so that it just doesn't get lost. Yeah, but our focus is on deprecating Zcashd and preparing for CSAs and sort of NU6 and NU7 and all of the things that we've been talking about. And I don't think that the trailing finality work is disrupting that. And I'm pretty confident now in the security properties because we, as you'll see, we have sort of proofs of the most important properties. Okay, so why can we not just use proof of work? Why does plain proof of work not have this assured finality property? So first of all, you can partition the network. And I think this is an underappreciated point about Bitcoin's security properties or the security of Bitcoin-like protocols. That if the network is partitioned, then you basically have no security against rollback attacks. So you're still enforcing the consensus rules, but there's no way to prevent double spend in that situation. And the safety of a proof of work protocol is only probabilistic. So if an adversary finds lots of blocks in a short time, which they always can if they're lucky, then that would allow a rollback. The other thing to note here is that so the number of confirmations that you require in order to get security in a proof of work protocol is actually quite high because there's a paper by Greenspan and someone else that pointed out that Satoshi Nakamoto made an error in their analysis of the probability of attacks. And so the kind of consensus that you only need about 6 confirmations in Bitcoin is based on that error, basically. And you actually probably need about 10 or more to have reasonable reasonable probability that the adversary won't be able to do a rollback. So to solve these problems, we need to use a Byzantine fault-tolerant protocol. So what does that mean? Well, what's it doing in this case? It's allowing you to deterministically agree on the finalized chain, even if there's a network partition. Okay. Yeah, so Crosslink is based on this paper called the Ebb and Flow paper. So Ebb and Flow is a model of blockchains where you're trying to achieve a compromise between availability and finality. So this paper proposed the snap and trap protocol, which actually is very complicated and has some consequences that weren't really anticipated in the paper. I don't think they fully prototyped it, because if they had, then they would have seen that it doesn't actually work for UTXO-based blockchains. In any case, we basically solved that problem for Crosslink 2. And it compares quite nicely in complexity to other protocols like Gasper used in Ethereum. Ethereum 2.0. So how do you construct this? You take an existing proof of work, and to answer the question from before, this could easily be Bitcoin's proof of work as well. And you pick another BFT protocol that allows you to do proof of stake. And sort of modern BFT protocols, some of them are kind of focused on blockchains and designed to work in that setting. So they work very well with proof of stake. So yeah, you have this modularity that allows you to switch between sub-protocols if you need it. And we're going to call the proof of work chain and the BC protocol because it so finds the best chain. Each node looks at all of the valid chains that they can see, and they choose the one with the most work. But when you abstract that, you don't really need to consider the details of how the work is computed. You can just say that it's picking the best chain. Okay. So what is a BFT protocol? So this idea of Byzantine fault tolerance means tolerating adversarial failures, and you don't have reliable information on whether a component has failed. So if you did, then you could just exclude that component, and then it would be a much easier problem. But if the components are adversarial, then they're going to the adversary is going to try and make them look like an honest node, and you won't necessarily be able to tell the difference. So in general, this isn't possible without some constraints, and you have to make an assumption about the proportion of the resources controlled by the adversary. So this is a well-known result in distributed systems theory, so hand-waving a little bit, the adversary's share of the resources has to be strictly less than 1/3 in order to make this work. So why is that? So let's say that the nodes are voting for the next block, and if they have a 2/3 absolute majority, so for simplicity, let's say you have a fixed number of nodes, and that number is specified in advance. So you always know what 2/3 majority is, and that can be generalized to use stake. We'll explain why 2/3 in a bit. And the worst case for the algorithm is that you have a network partition. And so here we can see that 1/3, so the honest nodes have 2/3 of the resources, and because you've got a partition, the two sides of that partition are in the worst case only voting 1/3. And then you have this adversary. It has the remaining 1/3 of the resources, but it can vote on both sides of the partition. So the honest nodes are voting for two different blocks on it, on the two sides, and then the adversary is throwing in their votes for the same blocks on each side. But their blocks can be duplicated because so these honest nodes can't see this vote, and similarly, these honest nodes can't see these votes. And so on each side, you meet the threshold of 2/3, and so we have a fork. And you can generalize this to stake instead of number of nodes. So just to see that, so if the adversary's proportion was less than 1/3, the attack wouldn't work. So suppose now that the honest nodes have 3/4 of the stake, and the adversary has 1/4. So you need to do some sort of high school fractions here. The honest nodes will each vote 3/8 of the stake on each side. The adversary has 1/4, so this is what 9/24 plus 6/24 is 15/24 on each side, but 2/3 is 16/24, and so the attack fails because you don't have 2/3 of the stake on each side, and that's why it's a 1/3 threshold. Okay, so you might be thinking that a proof of work protocol, you need a 51% attack to break it. So is that better than 1/3? But remember that this, the BFT security analysis allowed partitions, and the proof of work one does not. And so if you have a partition in a proof of work network, then so let's say that if you were in some subset that are partitioned from the whole of the rest of the network, then the adversary can potentially control the majority of the hash rate just in your partition, and that doesn't require having any fixed proportion of the total hash rate. So it's just completely broken in that case. And this is a realistic attack. So if you read this paper, Hijacking Bitcoin, Routing Attacks on Cryptocurrencies, then it explains how it could be applied to Bitcoin. And Bitcoin did some protocol changes that kind of help a little bit, but it's not clear that they're sufficient. Okay. There's no problem in practice with the adversary voting on both sides, because so in proof of stake this is particularly easy because the ballots that they're voting with are just signatures, so you can duplicate them. Well, you can vote for two different things, and the BFT protocols, we're not going to go into details of how BFT protocols work. We're just using them as a black box here. So our security and performance goals, we want to, so this log is some sort of way of interpreting the state of the protocol as a sequence of blocks in this case. And we have that, we want, so logfin here is the finalized chain. It's the chain before the finalized block that we decide on. So that chain has rollback safety, assuming either that the BFT protocol meets its assumptions or the best chain protocol. And you do have to assume that the glue between them is correct, but you can sort of prove that unconditionally without additional assumptions, really. And this is true under partition. And it's live. In other words, the protocol sort of continues advancing, is able to generate new blocks under reasonable assumptions. And the latency of basically the confirmation depth of your finalized block under normal circumstances will be slightly over double the current Zcash. Okay, so if you were using 10 confirmations for current Zcash, then the finalized block would be sort of just over 20 blocks back. So that's quite a lot, but so you can imagine further improvements. And remember, this is true under very conservative security assumptions. And then, so you don't have to go back that far and get these extra security properties. You can just use the chain as is and have the same security as the current proof of work with the same confirmation depth. We also want to ensure that if you do that, then it's always an extension of the finalized ledger, and the gap between them is no more than some fixed number of blocks. And we'll explain why I think that's important. And then, so this lower latency option, it has rollback safety on the original assumptions about proof of work. And similarly, it's live. Interesting. So it's live. You have to make assumptions about both protocols for this to be live, but they are reasonable. So if for example that the BFT protocol was subverted in some way, then the whole protocol would tend to stall instead of carrying on unsafely. There's some detail there. So our proof of work protocol basically sort of has to, it's like a shark, it has to continue swimming, otherwise it'll die. Similarly, a proof of work protocol has to continue finding new blocks. Otherwise, an adversary will have an unlimited length of time to create a competing chain. And so, yeah, Crosslink is designed so that so when we say that the chains can't be more than L blocks apart, the proof of work chain is still continuing, but it's only producing empty blocks, or what we call safety blocks. Okay. And yeah, I've already said that this is just the existing chain with a few changes to consensus rules. So if we did let the this low latency ledger run arbitrarily far ahead, then that would have some undesirable security consequences. So if we allowed arbitrary transactions on the low latency chain after that point, then we could get arbitrary differences in balances. So if some parties are looking at the finalized ledger and some are looking at the low latency ledger, then there's no bound on how far the balances could be apart. And in that situation, you would have service providers taking different decisions about sort of how they would work around this. And that wouldn't necessarily be properly analyzed if it was an emergency. So you can define this safety mode, which probably in practice would mean that Coinbase only blocks. And then once you've resolved the stall, which might require some sort of human action to figure out what is actually going on and why, then it can be resolved. So this also means that, so say that you found a serious security bug, then the validators on the proof of stake side, if you had enough of them agreeing, then they could agree to essentially put the chain into the safety mode until a mitigation for the security flaw could be applied. And what I'm suggesting is that we may want to define a specific governance policy for that in advance, so that everyone has a clear expectations about what's going to happen in that case. And there's, if you look at the TFL book, then it gives more motivation for that. Okay, but why do we want for now to retain Zcash's existing proof of work? Yeah, I've already really gone through this. We want to be tolerant to weaknesses in the BFT protocol. So some of these protocols are really quite complicated, or failed assumptions. So if in the initial stages of a switch to proof of stake, you don't have very much stake, it's possible that some party could have enough to violate the 1/3 assumption, then you have this fallback in terms of proof of work. Yep, and as I said, the finalized chain will have in practice about double the latency of the lower latency chain. Yep, and yeah, if you don't require finality, then if it stalls, then you can continue on. Okay, I'm getting notifications on my phone. Let me just check. Yeah, that's fine. So yeah, stake-weighted BFT protocols. So we have some validators. They each control some proportion of the stake, and this can be dynamic, by the way. And you have proposals to extend. This is the BFT chain, which is not necessarily the same as the the transaction chain that we're trying to implement at L1. And they have to be voted on by so this is important, an absolute 2/3 majority of the stake. So in any given epoch, we need to know how much stake there is, and then prove that the validators representing at least 2/3 of that total stake have voted for the proposal, not 2/3 of the validators who actually vote, because that wouldn't be skill. And then there's a rule associated with the BFT protocol about which BFT chains are final. So because of message delays mainly, it's possible for there still to be a short fork in the BFT chain, but the protocol is designed so that it's possible to yeah, those are only ever short-lived forks, and they don't affect finality. Yep, and it's possible for the protocol to stall if there's network partition, because if you don't have 2/3 of the stake voting for any given proposal, then it will effectively stall. And there have been examples of that. For example, in Ethereum, there have been short stalls. Okay. I'll skip over this actually, because this is going into so some of the flaws that were in the Snatham chat paper that this was originally based on, and they're basically completely solved by Crosslink 2, so we don't need to go into them. Okay, so how does it work? You have so basically the existing Zcash protocol is preserved exactly as is with mining, with the same block headers. We'll add something to the block headers. And in addition to that, you have the BFT protocol managing a parallel blockchain. And these BFT blocks, they just have a header. They don't have transactions themselves. And the existing blocks, we'll call them BC blocks just to disambiguate. So we have a confirmation depth sigma, which is fixed as part of the protocol. And so as I said before, you have this crosslink structure between the proof of work chain and the BFT chain. And so each BFT block is going to point to a best chain block. There's a question in the chat saying, is there a paper written for Crosslink? So there is just the TFL book. There is no paper. It absolutely is a publishable protocol, and sort of if I had time, I would write an ePrint for it. But I probably don't have time to do that. I think actually it would be a good idea to write a paper. Yeah, so it's actually easier to see this from diagrams. Okay, so at the top here in green, we've got the best chain protocol. And this could have forks. We're just considering the simplest case so that we can explain what happens. So we have references from each best chain block to a BFT block. So this is the, I'm assuming that you can see my cursor. So this on the right is the tip of the best chain. So we go back, so 3 in this case. So sigma is going to be 3. I didn't write that down. 3 blocks, and then so we go to we follow the reference to the BFT chain, and then we follow it back to the best chain protocol. And that's essentially why we have the double latency. So so given that this is the most recent block on the tip of the proof of work chain, this will be our final block in this case. Okay, so yes, so this is referring to yeah, so you would add a reference to a final BFT block to the best chain block header, and you'd include so you ensure that this necessarily points to a final BFT block. And how you do that in practice is you refer to a later sort of context in which the block you're pointing to is necessarily final. So it's kind of a proof by construction that it's final. And then similarly, you in each BFT block, which remember is just a header, you refer to a sigma confirmed BC block. So how you implement that in practice is you give sort of sigma block headers after the one that you want to point to. And so the way that we unify BFT block proposers and miners is that whenever you mine a block, it is implicitly proposing the block sigma blocks back. And so these proofs are implicit, and they don't add much complexity to the protocol. Okay. So yeah, if we follow the reference from this, so here is the sigma confirmed BC block, this one. Follow it to the BFT chain and then back. That is the finalized block. So why does this work? And so this is the lower latency chain. So that this works exactly like we have just sigma confirmations. And so we construct the protocol so that the block at log fin is always an ancestor of the block at log VA. So one of the innovations that this has over SAP and chat is that we're defining objective rules for which BFT blocks are valid. So we're not relying on the 2/3 majority to do that, because every node is independently checking these rules. And that's what allows us to make very weak assumptions on the BFT protocol. Yeah, so in order to prove that a block is sigma confirmed, we just give sort of sigma headers following it, and that proves that the corresponding amount of work has been done on the BC chain, because we also check the difficulty adjustment algorithm for those proofs of work. And so, yeah, I said this before, so to refer to a final BFT block, we give a context, and then it's objectively defined what the last final ancestor on the BFT chain of that block is, and we use this notation LF. Yeah, and that ends up doing what we want. So here are the extra rules written out completely formally. I'm actually going to skip over the security analysis because I only have 10 minutes left, and I want to give time for more questions. But you can see that the extra rules fit on the slide, so that's good. And yes, we can. So here are the security assumptions. You can see mainly here that they're very simple. So I won't try and explain the notation here, but actually, so this symbol means that these chains are consistent with each other. So what we're saying here is that the security property we need from the best chain is that if we truncate the views of any two nodes I and j by sigma blocks, then those will be consistent with each other. In other words, one will be a prefix of the other. And so similarly for the BFT protocol, except that we're using this this last final function instead of truncating the chains by sigma blocks. Okay, and we also have to assume the 1/3 sort of bound on non-honest votes, and this is the result we get. So we achieve the same safety property for log fin from either of two assumptions. So either we assume this property of the best chain, or we assume it from BFT protocol. Skip over that. Yeah, I'm going to skip the proofs, and you will need to look at the slides if you want to go over those in detail. Yeah, but the security proof for safety fits on 2 slides. So this is basically half of it, and this is the other half. And yeah, if anyone wants to sort of go over the detail of this and be convinced that it's correct, I'm happy to go through it with them on Discord or in the chat on Hoover. And we can sort of similarly for liveness, and that fits on 1 slide. So what's next? So we have a simulator written in Python, and that simulates a network of nodes. It's a discrete event simulation. In other words, the actual simulation is single-threaded, but it's simulating time and simulating concurrency between nodes. But it's deterministic, which is helpful for reasoning about attacks. And so the aims of doing this simulator is to show that the protocol works at all. Its consensus rules are well defined. So to clarify how it works with the BFT protocol, simulate partitions and delayed messages and so on. And importantly, to simulate attacks. Yep, and I think there is already a PR open which basically completes most of the simulation. There's a little bit more work to do. And then we need to implement some simple attacks. Okay. Yep. Yeah, that's the graph of what we need to do for the simulator. So there was a question in the chat: does a proof of concept for Zcashd or ZebraD exist, or is it planned? So it's never going to be implemented for Zcashd because it would be a major feature, and we've already said that we're not going to implement any major features for Zcashd. But for Zebra, yes, there is a plan to implement this initially using a dummy BFT protocol, which works because we even a dummy BFT protocol, you retain the security of proof of work. And so here are the tasks that we would need to do for that. We define the interfaces, sort of there's some design of block header formats and peer-to-peer protocol changes and so on. So that's the work that needs to be done there. Open design issues. I should really have left more time for this, shouldn't I? So selecting the proof of stake protocol. So the open questions here are: so which BFT protocols would give the most bang for the buck in terms of sort of integrating with other ecosystems? So how secure are they? Are they implemented in a way that's easy to integrate and so on? So will we need to adapt the protocol in order for it to work? So in this framework, and importantly, how many validators do we need to support? Because if we only have a tiny number of validators, then we're basically wasting our time, because the whole point of this is to decentralize the reliance, so that we don't have a small number of mining pools that could potentially collude together. We want to define governance policy for the safety mode. And there's lots of questions that need to be answered about how issuance and staking should work, what proportion of issuance should go to staking versus mining, and so on. The privacy for staking and so on. And so our plan is to prototype this on transient testnets. If this ends up being something that we spend a lot of time on, but so we've kind of The plan is that this is not something that needs to necessarily be done by ECC. It could be done as part of a grant. We're just putting the design out there and saying we think this is a good way of doing it. And I would imagine this would have to be funded by a grant. Okay. How can you contribute to this? Here's the TFL book, sort of open issues, criticize the design, say if you think this is a complete waste of time, then say so. I personally think that it's going to be important in the long term to move to pure proof of stake, to remove the environmental impact of proof of work. You may disagree, but we want to know your opinions, and we want to know, we want to have input into the design of staking issuance. Okay, so I've gone through questions as we've gone along, and I will answer any remaining questions on Hoover. Thank you.